Hello, I'm Kartik. I'll talk about our recent work on quantum Hoare type theory. We know that quantum programming is inherently imperative and difficult to reason about. Uh, it is imperative because we apply a sequence of gates that manipulate quantum state each. We do measurements which can destroy quantum state, for example, and we also prepare state, which is also a stateful, effectful operation. In classical programming, Hoare triples are a way to reason about change in state. So here is a Hoare triple, PCQ, where C is the command to be executed and P and Q are pre and post conditions on the state. So the way to read this is if P is true for the state and command C is executed successfully, then the post condition Q will be true on that state. Uh, We also know that in pure functional settings, it is easier to reason about programs, but we do not have access to state easily. For example, a typical functional programming language like Haskell. The way to get over that restriction is by using monads, which encapsulate the result of computational effects and give you a clean interface to work with state in a purely functional setting. The question is, can we combine Hoare triples with monadic types? And the already solved answer is yes. It has been done before in Hoare type theory uh, in late 2000s. And in this work, we are trying to answer this question for the quantum setting. So here is an overview of my talk. Next, I'll talk a little bit about both Hoare type theory and quantum IO monad, which form the foundation of our work. And then I'll introduce our own contributions, present some ongoing work and future work, and then conclude. So let's look at Hoare type theory, which was introduced by Nanevsky et al. In late 2000s. So here's a Hoare type. Hoare types encode pre and post conditions in the type themselves, and being dependent, they are very expressive. So let's try to read this type. So P and Q are pre and post conditions, as we saw before. Uh, we have the return type, A, and it's given a name X. And then delta and psi are variable and heap contexts, respectively. Here's an example to show the expressive power of Hoare types. We are showing the alloc primitive from classical HTT or Hoare type theory. Uh, we see that this it works on all types alpha. That means it is polymorphic. It takes X as input of that type alpha, and we say that this is a pi binder, which means it is a dependent type. And anything here can depend on this value X of type alpha. So now looking at the precondition, it says emp, which means the heap is empty at the beginning of this program before it is executed. The post condition is y points to x of type alpha, and that's the output, the result of the stateful allocation command. You expect that when you call alloc on an input x, it returns you a location y of type net in a heap in which y now points to x. So the question is, can we do something similar in quantum setting? So for that, we will need some certain primitives similar to alloc here. And that's what brings us to quantum IO monad, which was introduced by Alton, Kirsch, and Green in late 2000s as well. And it is a monadic interface implemented as a Haskell library for doing quantum computation. And it has a lot of neat things that we need to make our quantum Hoare type theory work. So uh, the core idea is that there is a monad called QIO, which is indexed by the type of the computational result. So we see some examples here of primitives. So make qubit is a primitive, which takes a Boolean and returns a qubit. And we can see that the result is encapsulated in the QI monad. Similarly, there's a measurement primitive mesqubit, which takes a qubit and returns a bool, again encapsulated in a QI monad. And then there's this unitary application primitive apply u, which takes a unitary and it returns unit because you do not get a value out when you apply unitary. It only results in a change of state. And QI is also very expressive in terms of what you can do in quantum settings. So, and this is because they provide two primitives, one for creating arbitrary rotations and another for doing controlled operations. So a rotation primitive takes a qubit and a description of a matrix uh, of, that can define the unitary and returns the unitary. So here the first argument bool comma bool specifies an index and sees the type of complex values. So using this you can define what a unitary matrix can do as a function. So this lets you specify any single qubit rotation. Now for if Q, it takes a qubit and a unitary and returns another unitary in which the first argument becomes the control. And that lets you define controlled gates such as C0 or Toffoli. We should mention that use a monoid and QIO interface with sequencing or matrix multiplication as its operation and identity as its neutral element. So this gives us a very clean interface to work with. Now let's talk about our own work, quantum Hoare type theory or QSGT, and we will look at some examples first. The core idea is that instead of just indexing the QI monad with the result of the computation, we also index it with pre and post conditions, similar to a Hoare type we saw before, and we can call it a Hoare monad or a Hoare type. So here is an example of a trivial function, hello quantum word, and we see the precondition on it is empty. It returns our result of type Boolean, and there's a postcondition empty and id of r and false. Id means identity, and we are saying that in the output, when this function returns, the value r will be equal to false. And here's the body of the function, which is exactly the same as in the QIO interface. And QIO, since it's implemented in Haskell, you can read this as Haskell code with do notation. So we are binding xq to the result of this make qubit operation on false, and then we are applying the measurement primitive on q. And as humans, we can reason about this very easily. We can say that, yeah, initializing a qubit in false state and then measuring it will give us false. And there is another program here, just a little bit more complicated than the previous one, where apart from doing this initialization as before, we also apply a Hadamard gate on Q and then measure it again. This time, the postcondition is fairly trivial. It just says the heap is empty. And we know that to be the case because H will put the qubit into a superposition of 0 and 1, and we can expect either of those to be the outputs. But the question is, how do we mechanically reason about these programs? And that's where Hoare type theories, type system, and reasoning techniques come in. So let's talk about them now. What we really need to do is we need to change the primitives like we saw alloc before in Hoare type theory to support quantum primitives. So I'm showing an example of initialization primitive here. And the way to read this is as before, x is bound to the value written by make qubit m, and then sequence with other commands that will follow. And x will become available to these commands to refer to. This is like a monadic bind. I should also mention that SGT uses bidirectional typing for inference, where the convention is When we write E left arrow A, and I've colored it in blue, it means expression E checks against type A. And when E right arrow A, it means expression E synthesizes or infers the type A. So let's look at the typing rule. And here is what we want to check. The term X bound to make qubit M followed by E, and it works in the context delta, which is the variable context, and the precondition P. What we want to do is generate the strongest postcondition for this term, and that postcondition will be uh, this postcondition Q. So in order to do that, the syntax directed typing system, which we are showing here, needs to do certain things. So first of all, it needs to verify that the term M here has the right type pool. So that can be checked. Apart from that, it needs to make sure that these two commands compose together properly. So we need to we need to synthesize the type for E, that is synthesize the strongest postcondition Q for E. So here we are seeing delta P, and the term has changed to just E. So to be able to do that, what we do is we add X, which is bound here in the variable context. And for in the precondition will also change since we are executing make qubit M and moving to the next instruction, next command. So we extend the previous precondition with the strongest postcondition for this operation, that is make qubit M. And let's read the postcondition. It says X points to some state representation of the M term that was given to us. And we know that M being a Boolean, it will be either cat0 or cat1. Let's look at another primitive, measurement. And the reasoning works about the same in the same manner. We have mass qubit here. We have the strongest postcondition we generated, Q. Oh, I forgot to mention this existential quantifier here. So in the previous slide, the X's type was qubit, and in this case it's bool, which is what we would expect because the measurement result of a qubit should be a Boolean. So it is needed here because otherwise we will not be able to talk about X in the postcondition. And proceeding with type checking for this conclusion, we first need to check the type of the term M. It should be qubit. And then, like before, we will check or generate the strongest postcondition for E given the extended context delta with X. And P will be followed by a strongest postcondition. So let's see what that will be for measurement. So here, this is the strongest postcondition for measurement, where what we are really saying is that M points to something, that is, it is allocated, and this symbol, lollipop symbol, means that it gets changed to empty. That is, the M qubit, for an example, gets deallocated, and that part of the heap becomes empty. So that's the strongest postcondition, but there is more. We also need to generate a verification condition that says that in the context delta and the state or heap context psi, the precondition P should imply that M was actually allocated. So this symbol just means that in our heap, M was allocated to something. And these are just two operations we will need to see for this presentation. Now let's talk about how the verification will work. So our Hello Quantum Word program is reproduced as before, and let's step through what is happening at the logic level. So we start out in the precondition emp, which is specified in the type. Then when we step through, the precondition for the following command, measure qubit here, gets expanded, and we get the strongest postcondition for make qubit appended here. So now q is pointing to ket 0, as you would expect for make qubit false. And finally, when you do measurement, this qubit q that was pointing something becomes empty. Um, so this gives us some idea of how the system keeps the track of postconditions being generated. And but the job is not done. Um, we want to be able to say that if you were able to type check this program, it means that the pre and post conditions you applied were correct. That is, the program meets those expectations. So the general idea is that after generating some verification conditions, as we saw in the previous slide, we need to uh, prove them correct. And that can be done using an automated theorem prover or even interactive. So let's look at the next example as well. And the first step is the same. You start out with empty heap, then you create a new qubit, which will change the heap to q pointing to 0. And then there's a new operation here where we are applying Hadamard. So even though we did not see the rule, we expect it to be something like this. We say that in the heap where q was pointing to 0, change that to q pointing to plus, ket plus. Uh, and finally, when you do measurement, you can again apply the same postcondition where q pointing to something becomes empty. And this is the same as the postcondition we wanted in the uh, type of the program. So this was a little preview, and I would talk about what we are doing right now and some future work. So one issue with our current theory is that it looks like simulation, which can be very expensive, and we are not very interested in that. So we are looking at tractable semantics for unitary application. And Matthew and me proposed this really neat idea of path sum actions for unitaries and 2 years ago. This was based on Feynman path integrals, and we think that this might be a reasonable approach for a limited subset of quantum programs that are interesting. Another advantage of this technique is that it also can serve as a quantum assertion logic in the sense that the way you specify um, correctness specifications in Amy's work looks very much like how mathematicians write correctness for quantum circuits. But we're also interested in other forms of assertions that we would like to be able to specify in our framework, such as is a quantum state entangled, or if it is an equal superposition. Another interesting line of work is integrating linear dependent types into our framework, and Peter Selinger's group has recently proposed a new version of Protoquipper called Protoquipper D, which has linear dependent types in it. So I look forward to exploring that and trying to integrate that system in our framework. Um, Another line of work we have thought about is how quantum circuits really correspond to the notion of arrows in category theory and, for example, in Haskell. And there is previous work from 2006 where people have treated super operators as arrows. So we look forward to trying to see if we can generalize our Hoare monads into some sort of Hoare arrows and treat the quantum circuits directly. And something very interesting that we are actually working on right now is the idea of more fine-grained types for quantum computing using behavioral typing techniques, where we have explored resource theories in a previous draft with my collaborators. And even at this QPL, we have another paper where we propose Gottesman types based on Heisenberg representation of quantum mechanics. To conclude, we have combined ideas from classical Hoare type theory and QIO functional monadic interface for quantum computing to design our quantum Hoare type theory, which is a dependently typed language with support for reasoning about quantum effects. Uh, we have a lot of ongoing work right now, but we have hope that this could be a unified framework where you can do both programming, specification, and reasoning about the programs. So we are very excited, and there are several challenges ahead. Please see the paper, and I would love to talk more. Happy to take questions now.